In this video, we're going to look at solving some definite integrals. In the previous video, we had indefinite integrals, and those were functions. Definite integrals, you're going to have numerical values. Our first example, we're going to integrate 6x squared minus 3x from 1 to 3. If you were to graph this function and look at its area between the curve and the x-axis, but specifically between the values of 1 and 3 on the x-axis, we're looking for the area. The antiderivative is when you add 1, you get 3. 6 divided by 3 is 2. Negative 3x, its antiderivative, you would add 1 to the power to get x squared, divide by 2. 3 is not evenly divisible by 2. That's fine. It's just 3/2 x squared. Now, with lower and upper limits, you want to substitute these in using fundamental theorem of calculus. Your antiderivative with the top number subbed in minus the antiderivative with your bottom number subbed in. Carefully calculate. 3 cubed, that's 27 times 2 is 54. 9 times 3 is 27 halves. 2 times 1 cubed, that's 2. Minus 3/2 times 1, minus 3/2. Just be careful subbing these, or excuse me, not subbing, typing these into your calculator, and you get 40. An example using trig would be the integral from 0 to pi of sine x minus 7. Take the antiderivative of sine x, that's negative cosine x. The antiderivative of negative 7 is negative 7x. Sub in pi for your variable, minus, sub in 0 for your variable, and make careful calculations. Cosine of pi is negative 1, so negative 1 is a positive 1, minus 7 pi, minus cosine of 0 is 1, so negative 1, minus 0. Subtracting negative 1 is the same as adding 1. 1 plus 1 is 2, minus 7 pi. If you're asked to approximate, you would type this into your calculator and approximate to the appropriate number as asked in your homework problems. Let's check out an absolute value integral. We're going to integrate from 0 to 4 the function absolute value of 2x minus 1. The absolute value of 2x minus 1, if you set 2x minus 1 equal to 0 and solve, you get 1/2. Absolute value is defined as, for this one in particular, we'll have a V-shaped graph with an x-intercept at 1/2, and that's from setting this equal to 0 and solving. The graph behaves like the line 2x minus 1 as long as x is greater than or equal to 1/2. The graph behaves like 1 minus 2x as long as x is less than 1/2. Absolute value functions are piecewise functions. That also helps us integrate because we can integrate in pieces. This little bit here, shaded in the graph, belongs to the 1 minus 2x portion, and it's shaded from 0 to 1/2, and that is where you integrate 0 to 1/2, 1 minus 2x. Plus, then when you switch to the other piece of the function, you're going to integrate from 1/2 to 4 of 2x minus 1. That's that second definite integral. Okay, so our antiderivative is x minus x squared, and we're going to evaluate that at 1/2 and 0. The other piece, the antiderivative is x squared minus x, evaluated at 4 1/2. Back to the first part, 1/2 minus 1/2 squared minus 0 subbed in is just going to give us a 0. In the back half, 4 squared minus 4 minus 1/2 squared minus 1/2. 1/2 minus 1/4 is 1/4. 12 minus negative 1/4, because that's a fourth minus a half. 12 minus negative 1/4 is 12 plus 1/4. That's 49/4. Added together is 50 over 4, which reduces to 25 over 2. And that's the total area from 0 to 4 for the absolute value of 2x minus 1. There's another property, like the one we just looked at, where you can split a continuous function into several definite integrals, and as long as you keep the border numbers matching, you're going to be okay. For this one, if you happen to have a function that when you graph it, if you graph it, happens to be an even function. Now, even function is a function whose graph, if you were to use the y-axis as the spine of a book, you could close the book and each side, the left side would touch the right side, or vice versa. They're mirror images across the y-axis. And yet another way to say it is y-axis symmetry. If you have an even function and your integral limits are evenly spaced, you can double the integral and only integrate halfway. By doing this, it allows us to take out negative pi over 6. And what we'll do is we're going to find the area from 0 to pi over 6, but we'll double it. That way it has the same amount here as it would over here. The antiderivative of secant squared x is tangent x. Don't forget times 2, because we're doubling. 2 times tangent of pi over 6 minus tangent of 0. As a refresher from the unit circle, tangent of pi over 6 is the y over x. That's square root of 3 over 3. Tangent of 0 is 0. So our final answer is 2 times the square root of 3 over 3. And then our last example, the integral from 0 to pi over 4. And this is one where we can use a handy trig identity to make our problem easier. The Pythagorean identity sine squared theta plus cosine squared theta is equal to 1 can be transformed if you subtract sine squared theta from both sides. If you do that, cosine theta is equal to 1 minus sine squared theta. This numerator can be translated or swapped out for cosine squared theta. Now we get a 1. The antiderivative of 1, d theta, is just theta. Sub in pi over 4 minus sub in 0. Pi over 4 minus 0 is pi over 4. I hope this video has helped you. Reach out by email or phone. Come by the office as needed, and I will do my best to help you out.